Alright, now let's look at singular value decomposition. Yeah? In the linear algebra refresher, we mentioned or we learned that a matrix is a linear transformation in space. Yeah? We've seen some examples, but here we get another example. You have a vector, column vector 1, 3, and you have a matrix. A is a 2 by 2 matrix. And we're going to let the matrix A work on the vector X. Yeah? So the vector X, we have 1, 3. Yeah? This is this vector. Let us here we go. This is the vector X. So if we let the matrix A working on X, this we can do because this is a 2 by 2 and this is a 2 by 1. Right? So this should be a 2 by 1, a column vector. How much is it? Well, we're gonna calculate is 2 plus 3 is 5. And we have minus 1 plus 3 is 2. So the new vector is 5, 2, 1, 2, 3, 4, 5, and then 2 here roughly. Okay? So that is the new vector. As the new vector y. Yeah? That we get if we let this matrix work on X. Now if we look at it, what has actually happened? Yeah? What does a matrix transformation do? Well, the first thing it does is it rotates. It rotates by an angle theta, so it becomes in line with y. But you see it's shorter than y. So it does not only rotate, it also stretches. So what does the matrix transformation do? It rotates and it stretches. Okay, so let's see if we can derive a formula for this. Let's start with a pair of vectors, v1 and v2. Yeah? But you know, in the general case, you will have n of these vectors. And these vectors are orthonormal. Yeah? That means that these vectors are unit vectors and they're perpendicular to each other. That means orthonormal. Then we're going to have a matrix transformation, and we said that we would rotate and stretch. And then you get another orthonormal base with the unit vectors, the u1, u2, and so on till un, right? And then we're going to stretch it. And in order to stretch it, we will apply these sigmas here, sigma 1 to sigma n, and these we call the singular values. So they represent the variation in the data. So we have the rotation of the v1, v2 into u1, u2, and then we stretch and we get sigma u1, and the red one is sigma u2. It's sigma 1 u1 and sigma 2 u2. Okay? So what we basically want is we have a matrix working on an orthonormal series of vectors. Then we have another series of orthonormal vectors which take care of the rotation. Yeah, you can see it here, but you can also see here that v1, v2 has rotated to u1, u2. And then we're going to apply the stretching. Yeah? The stretching, you will have the stretching factors on the diagonal, and all the other items are 0. So how can we write this now a bit more formally? So let's call this the vector v, and let's call this the vector u. Then we have that AV equals u sigma. Yeah? So this vector here we will call sigma, capital sigma. What we're going to do then is we're going to multiply by the inverse of v, yeah, on the right. and we do exactly the same on the other hand. Now, V times the inverse of V here, that is the identity matrix. Okay? So the identity times A remains A, and then we have U times sigma times V minus 1. But because V is an orthonormal vector set, yeah, the inverse of V is equal to the transpose of V. Yeah? This is a characteristics of matrices related to orthonormal sets of vectors. And so we have now that a matrix n by n A, yeah, we can break this down to three simpler matrices that actually do rotate, stretch, rotate. Yeah, this is the basic concept. So you have a matrix working on a vector. This can result in a complex transformation, but we can decompose the matrix in three simpler matrices and get the same end result. Yeah. The nice thing about singular value decomposition is that it always works. Yeah, it's not like, for example, to calculate an inverse of the matrix need to be squared and so on. Here not. Any matrix can be decomposed in these three matrices. Okay? So A is a general n by n matrix. U is orthogonal and squared n by n. Then the sigma is n by m. And V is m by m. Again, squared orthogonal. Okay, so now let's see how we can actually calculate these U's and these V's.